the APP, or the auxiliary power plant. Pick up with the intake, turbine section, and then the combustor. Just like our T64 engine, the combustor section is the combustion section on the T64 engine. Combustor is going to kind of get our fuel air mixture, and then once we develop that heat, we're going to use all that energy to back drive a shaft all the way back through the center, back to our accessory gearbox. So on the front side of the combustor assembly, we have our fuel nozzles, 6 fuel nozzles, and then down at the very bottom at 6 o'clock, down here we have a thermal couple. It's fine, there you go. And our thermal couple here is what's going to give us our 621 degrees Celsius for over temp. It's also going to control our exhaust gas temperature gauge in the cockpit, tell us where we're at. On the tailpipe, we have our 204 degrees Celsius switch. This, in conjunction with 92%, which we're receiving, 92% is coming off from our speed switch here, right on the side of the accessory section. And the speed switch is kind of a dual-purpose speed switch. It's going to sense 92%, and that, in conjunction with the 204 degrees Celsius, is going to allow us to close the valve on the bleed air bottle. And then once the valve on the bleed air bottle closes, all bleed air coming off the turbine section is going to come back through and go down to the clutch for smooth clutch engagement. The speed switch also is going to register when we have 110%. It's going to pop our circuit breaker down there on our control panel, one of our automatic shutdown features. TAC generator, it's going to give us our RPM indications in the cockpit. And then below the TAC generator, we have our oil pressure switch. It's going to give us our automatic shutdown feature for 6 ± 1 psi for low oil pressure. And then internally inside the accessory section, we have our oil pump, and you can kind of see the channel here for the filter and pump. And below that is our sump dipstick, where we can check the oil. All right, moving back up top, fuel filter along the top side, and then we have our run-start solenoids. Our run-start solenoids are both going to initially open when we start the 8, and if you look here, you see the small line and a larger line. Small line being our start line, larger line being our run line. Both again are going to open when we initially start the 8, but once we hit 92%, our start fuel is going to close, and we're just going to leave our run fuel open. Fuel pump and fuel control. If we trace our lines out, we'll see that we have one additional fuel nozzle. So we had our 6 fuel nozzles around the front face of the combustor assembly, one ignition plug or igniter coming off from our ignition unit, and then we have an additional start fuel valve here right in the side of the combustor assembly. All right. On this side of the accessory section, on this side of the accessory section, we have our APP control generator. We like to nickname it our sandwich generator because where it sits in between the accessory section and the APP start motor. So APP start motor receiving hydraulic pressure from the accumulators, number 1 accumulator, back here. And our accumulators are all pressurized with nitrogen and hydraulic fluid, pre-charged at 1650 ± 50, being reserviced from the Utility 1 hydraulic system. So number 1 accumulator stands up right on top of the APP start valve manifold, and our number 2 accumulator lies down along the starboard side of that accessory gearbox compartment. Again, nitrogen pre-charged 1650 ± 50, and then compressed with hydraulic fluid compressing that pre-charge. So that when we pull the start lever in the cockpit, number 1 accumulator is always going to be aligned to discharge. There's nothing we can do. We can't stop that. That's going to happen. If we want to bring the number 2 accumulator into play, we have to pull the T-handle just after the personnel door above the APP hand pump and selector valve. Once we pull that, we're now opening up the path to bring number 2 accumulator in. If we've already discharged number 1 accumulator, then the number 2 accumulator is going to come in and start the 8. If we haven't, then we've lined it up that we can use the 2 of them at the same time. Now, they're not necessarily going to discharge at the same time. They're going to discharge piggyback to one another. Number 1 would discharge, followed by number 2, giving you a longer start cycle. Cases where we would use that is probably cold weather, or perhaps we notice when we look at the ADB, that the aircraft has a discrepancy with starting. APP is slow to start, stuff to that nature. All right. I think we pretty much get everything in this compartment. We talked about the clutch reservoir with bleeder coming down to the clutch engagement, clutch for smooth engagement. So if we look, we'll see that drive shaft coming through the firewall, making contact with our clutch. Again, 92% and 204 degrees Celsius. The key with the 204 is just telling us that we've got some kind of temperature on our tailpipe. So like your car, when you start it up in the morning, you see the heat rise off your tailpipe, you know that the engine's running. So at 204 in combination with 92 is our indication that we should have clutch engagement. We notice our APP on light come on in the cockpit at 92%. We have 4 seconds for clutch engagement. The way we know we have clutch engagement is we have our number 1 and number 3 generator on the forward face of the accessory gearbox. Within these generators, we have a little thing called PMG, permanent magnetic generators. So with the switches in the off position, if the accessory gearbox is spinning, we're going to get a caution light. Number 1, number 3 generator. We would also receive the number 1 and number 2 rectifier caution light. So once we receive that APP on light at 92%, we can kind of do a little count. 1, 2, 3, 4. We should see those 4 caution lights come on. Number 1 generator, number 3 generator, number 1, number 2 rectifier. If we don't, then we know that the clutch did not engage the accessory gearbox. We'd have to shut down. All right. Some other things that are manually we would have to actually shut the APP down for. No RPM indication, so if we're not receiving anything from the TAC generator on our gauge in the cockpit, we'd have to shut down. Acceleration hang-up. Maybe the RPM runs up to 20%, 30%, and it lags, stays there for 3 seconds or more. Then we want to shut down for acceleration hang-up. And then, of course, if we bypassed any of those automatic shutdown features, if high EGT exceeds 621 plus 621 degrees Celsius, without the circuit breaker pop, we would have to actually abort that start. Then we're looking at the things we have to watch for. Once we get the AP online, we've got caution lights. We're going to look for. We've got 3 accessory gearbox caution lights. It's going to cause us to shut down the AGB or the APP. One would be low oil pressure coming from this sensor right here, this pressure switch. Another one would be AGB chip light. An AGB chip. We've got 2 chip detectors, one underneath the clutch itself for oil returning to the clutch. Let's see if we can get my laser on that and show it to you. There it is right there. And then the other chip detectors on the back side of the accessory gearbox. And I'll trade positions with you. So right here. And then the next thing that we would have to shut down for was if we have high oil temp. And there's our temp. Right here is where we're going to get our temperature reading. This is our plug stat that's going to come down to our gauge in the cockpit and tell us whenever that temperature exceeds 145 degrees Celsius. All right. Other things up here in this compartment we didn't really talk about, but flame detectors for the APP. We've got 2. One on the firewall facing forward, scans 90 degrees, senses light equivalent to infrared. And then another one that would be between the APP and your cabin heater, which sits all the way down on the deck. Extremely hard to see unless you're looking underneath from this side all the way forward. You can see it shines back aft. Here in the trainer, it sits right here underneath the APP, but actual on the aircraft is way up forward up in here. It's hard, difficult to see. And then of course we have our engine fire bottles. Number 1, number 3. So this is main for number 1, main for number 3, and this is main for number 2. And then this is our APP. Difference between the APP fire bottle and the other 3 fire bottles is the APP is mechanically activated. Pull the lever, the T-handle in the cockpit, it's through linkage, it's going to discharge the fire bottle. So with the APP, we have fire detection with our flame detectors after 92%. We have fire protection 100% of the time. Our engine fire bottles, all electrical. So we had to discharge, we would have to use our engine T-handles. We would have to select the path of where we want those to line up. Last T-handle selected is going to be our path. So if we pull number 1 engine T-handle and then turn around and pull number 2 engine T-handle, number 2 engine T-handle was the last one selected. We would be selecting, if we fire the main, we would fire the number 2 engine fire bottle for main. Its backup is the number 3. Vice versa, number 3 is main for number 3 engine, backup number 1. Number 1 is main for number 1, number 2 engine's backup for the number 1. Kind of just goes around that clock, if you will. All right. Back here in the accessory gear, or actually we'll stay on the accessory gearbox. On the front face, we talked about our generators, number 1, number 3. We talked about our APP clutch, and then we've got our engine start motor. All right. Or actually, engine start pump. So our engine start pump is going to receive hydraulic pressure from the utility 1 hydraulic system, and then it has a solenoid on the top here that when we hit our starter, it's going to generate 4,000 psi going out to the appropriate engine start valve down to the engine start motor on the respective engine. If we look back here behind the accessory gearbox, we see our start valves. Number 1 engine start valve, number 2 engine start valve, and then on the back side is number 3 engine start valve. So once we hit that starter in the cockpit, our hydraulic pump, our engine start pump, solenoid's going to energize. We're going to produce 4,000 psi. Same time, the respective start valve is going to open. It's going to put the path of that 4,000 psi to the respective start motor on the engine to start spinning over the compressor section and start sucking in air and then mixing fuel. Behind the accessory gearbox on the port side, we have the utility 1 module. Grand Central Station, if you will. Everything's coming in, everything's going out. Underneath, we have our pressure and return filters. The forward one on the inboard side is our return filter. The one that's aft on the outboard side is our pressure filter. Not that that's necessary, but sometimes if you find one of these things popped, you feel underneath here. They've got a little pressure differential indicator, so when you're pre-flight, you want to slide your fingers through the opening here and see if they're popped. And you don't have to worry, there's no way you can reset those. They have to take, the container has to come out, bowl has to be flipped upside down in order to reset it. A lot of valves on the front side and back side is pressure switches, turn on, turn off valves, landing gear up, down control valves. Not necessarily we know what every one of those valves are, but some of the things I'd like to point out is back here on the back side, it's difficult to see on the aircraft, but here on the trainer. Here on the trainer with the drive shaft missing, you can look back in and see your emergency bypass valve. So, put a little light on that for you. So, emergency bypass valve, right there. That's what's going to pop up if we have to use our emergency extension system for the landing gear. So if we have to blow the gear down, so to speak, with the blow-down bottle that's in the cabin, this is going to pop up and it's going to allow any fluid that's in our drag struts that was on the retract side a path to come home. If we don't do that, we end up with a hydraulic lock and we won't be able to extend our gear. So when we're pre-flighting, we can stick our hand in here. If we touch this, it will go down. So if we stick our hand in here and we feel that fall down, we want to definitely say something to maintenance control. If we think that it popped down, it most likely did. All right. Behind that, we have 2 big filters sitting back here are for the engine start system. So engine start, going to filter its own fluid prior to going out through, kind of almost a self-contained system, if you will. Just draws what it needs off from utility 1. So using utility 1 as a replenishment, if you would. On the back side or aft face of your accessory gearbox, hydraulic pumps. You have your utility 2 hydraulic pump for your AMCM winches, for your tow boom, and then of course your Q24 davit or A-frame davit assembly. Directly above the pump is your utility 2 reservoir. A little different than your other reservoirs. It doesn't have the sight gauge, so to speak, for servicing. It's got a slide tube that's going to tell us with the respective rings on whether it's properly serviced or not. In the middle, right below the AGB drive shaft coming in from the main gearbox, is our utility 1 pump. Smallest pump on the back side of the accessory gearbox, but the system that has all the components or subsystems. And then to the right of that is our second stage hydraulic pump, just strictly for flight controls. Center line in the compartment in this forward hydraulics compartment is our utility 1 reservoir. The big guy, utility 1 reservoir, and then off to the side is our second stage reservoir. Now, a little different from second stage utility 1 and even with the utility 2, the second stage and first stage is identical to second stage. We have an accumulator, nitrogen accumulator, that's going to help to maintain the recharge on our reservoir to give us that constant head pressure down to the pump. Also, we don't cavitate our pumps and burn our pumps up. We can check the servicing on that accumulator by looking at the ground test panel right below the input drive shaft, and we'll look at that as we come back through. Below that on the deck, we have a second stage heat exchanger. It's a blower type heat exchanger. It's got features in it that's going to kick on and kick off automatically as our fluid temperature rises to certain specifications. It also has a safety feature where if the blower motor spins too long, it's going to lock itself out. It's going to go into a kind of a fail-safe mode so we don't burn it out. In either case, if the fluid gets too hot, we're going to get an oil hot light or second stage hydraulic fluid hot light. And we have to determine whether or not it's actually truly hot, 107 degrees Celsius, or is it really that safety feature of the blower locking itself out. And our NATOFS gives us pretty good protocol on how to go about doing that. Back in the very back, and you might want to go back around by the input drive shaft, is our utility 1 heat exchanger. Sticks all the way back there just in front of the main gearbox on that port side. So same style, it's that fan type radiator. Everything's going to require electrical power for that fan blower to kick on. And then back aft, just behind this second stage heat exchanger, we got a couple valves laying on the deck that are related to second stage. Look down through here. Put a light on. So the first one we talk about is that big one right there. That's our second stage isolation valve. All right. And first stage has an isolation valve just as well as second stage, and so does utility 1 have an isolation valve. So we'll talk about each one of those isolation valves independently. What they do. For second stage, the isolation valve is strictly to deal with the pitch locks. Normal operation, pitch locks are disengaged, we're ready to go flying. This isolation valve is open. Hydraulic fluid's going through the isolation valve to our main rotor servos, 3,000 psi, everything's fine. The first pitch lock advances. When the first pitch lock advances, this isolation valve closes, and when it closes, it's going to redirect that fluid to this little reducer right in front of the isolation valve. So when it comes down to this pressure reducer, now it's going to drop it down to 800 psi going out to our main rotor servos. So no longer going through the isolation valve because it's closed. It's going to force it to reroute through the pressure reducer back to our main rotor servos, and it's going to drop us down to 800 psi. Now, the reason for that is once we advance a pitch lock, we don't want to be moving flight controls around for fear that we're going to damage flight controls, damage other equipment. But we can't shut the fluid off completely to those servos just because of the weight of the main rotor head. If we were to cut the second stage to 0 psi, the rotor head's going to want to settle, the servos are going to want to settle, and we don't still do the same kind of damage we would if we were moving the controls around. So this 800 psi in theory is enough pressure just to kind of support the weight of the main rotor head and swash plate, hold ourselves in position. Alright, so really these two things only come into play with our pitch locks, only with our pitch locks. Normal operation, that isolation valve is open. Now when the first pitch lock advances, because the isolation valve closed and we no longer have 3,000 psi going to our main rotor servos, we will get that second stage main rotor servo bypass light. And that's coming from the pressure switch on the respective side of the main rotor servo. That's going to sense that pressure is no longer at 3,000, it's actually below 2,000 psi. It's going to trigger that caution light in the cockpit to come on. So we look for that. When the pitch lock advances, we look to see that we get that second stage main rotor servo bypass. In same fashion, when we disengage pitch locks, we've got them fully retracted and the pitch lock advance light has extinguished, we look to see that that light goes out, that that second stage main rotor servo bypass goes out to signify that the isolation valve has now opened back up and we have 3,000 psi going to our main rotor servos. All right. Mixing unit. It's got kind of two halves, if you will. It's got a forward section of the mixing unit right here, forward shaft, and then you got your aft shaft of your mixing unit. And if you notice on the aft shaft of your mixing unit, all of our linkage is coupled. Everything is connected for the most part to that mixing unit. This one's free to rotate. This one's free to rotate. So if you look at this, this is connected to our forward shaft so we can get independent travel on our roll system here. Or actually, I'm sorry, altitude system here. Pitch, and then roll, and all the way to the far side yaw. But forward shaft is where we're going to get that independent movement from each channel. Aft shaft, because it's coupled, anytime we move that collective, we're going to get that's our coupling action. It's going to get all of our servos operating together. And then off to the side, this is our collective bias pickup. And we'll look at that down in overhead a little bit better. That's our load signaling to hold the desired NF. That's going to sense when we move the collective, send a signal out to our respective engines, to the fuel control unit, to let them know whether we need more power or less power. And then on the inboard section, we have our yaw breakaway rod. It's got our shear pin. It talks about if we find binding in our yaw channel, we can shear with our collective. It talks about what pounds with AFCS, without AFCS, but that's our yaw shear pin that we'll look at on pre-flight. You always want to reach in there and see if you can feel that pin, make sure it's intact. Behind that, in that big rubber boot, that's where our limiters are and our stops for our yaw channel, our primary stops for our yaw channel, flight control channel. All right, so we'll pick back up with our second stage pressure manifold. All right. Everything that's going to happen with our second stage hydraulic system is going to come through this manifold. We've got a pressure filter. We're going to filter it before it goes out to the system, protect it. We've got a pressure switch right here. This is it's going to control our system pressure switch, or it's going to control our caution light for second stage hydraulic system. All right, 2,000 psi. Right above that is our actual shutoff valve. On our collective, when we say we want to turn off second stage, this is the sense or signal coming into the shutoff valve that's going to turn off this manifold, secure pressure going out to the respective servos that second stage supplies pressure to. Above that, right up here, we have another pressure switch, 2,000 psi pressure switch. This one is related to your AFCF servo system. This is part of that automatic transfer feature, where if we were to have second stage hydraulic system powering our AFCF servos, which we do normally in flight, servo 1, this is going to indicate 2,000 psi. It says, okay, yes, you can have servo 1 pressure engaged to power the servos. Now, if we lose pressure, and we'll show you where we get the sense of 650 psi, it will automatically transfer over to servo 2. If we try to come back to servo 1 from servo 2, it's going to look at this pressure switch first and say, hey, before I come back to you and give you pressure back to this system, we want to make sure you've got 2,000 psi available. So it's going to test that pressure switch. It doesn't test your system pressure switch that's controlling your caution light. It's going to test this switch that's going straight to your AFCF servo. So if we follow this line back, we'll find our pressure reducer. This is dropping our pressure from 3,000 psi down to 1,000 psi. So right here, pressure reducer, drops it to 1,000 psi. Then if we trace that plumbing around, there's our turn-on valve, if you will. Now the key with second stage is it's kind of a fail-safe system. So what does that mean? If we lose electrical power, it's spring-loaded to an open condition. So we turn off power at the end of the day, we shut the aircraft down. Regardless of what we've done on the AFCS control panel, when we secure the generators, we secure electrical power to the aircraft, this valve is going to go into an open state and say we don't pressurize. Designed that if we were to lose electrical power in flight, we'd still have hydraulic pressure to those AFCS servos if the second stage hydraulic system is functioning. All right, so what happens is electrical power comes on the aircraft, i.e. you turn the generators on. Once that happens, this valve is now in an open state. I'm sorry, it's in a closed state. It closes off. You reopen it by pushing servo 1. When you push the servo 1 push button, you're reopening this. So when you kick over to servo 2, you're telling servo 1 to close this valve off. Directly behind this is your 650 psi pressure switch for auto transfer. So if we have servo 1 selected as our system to pressurize our AFCF servos, we've tested it, made sure there's 2000 psi for the system. We've got our 2000 psi on the system. It comes through, reduces it to 1000 psi. Valve is in open state. We've got pressure going through to our AFCF servos. We've got servo 1 push button illuminated. If the pressure now drops to 650 psi, it's going to automatically swap over to servo 2. That's our automatic feature for second stage, and this is all the work that's happening for us. So when we're up here pre-flighting, we can look at that, look at our wiring, make sure the cannon plugs are connected, make sure there's nothing broken. All right, questions? Down here, right below the input drive shaft, is that ground servicing test panel for second stage. Quick disconnect couplings where we can hook up a hydraulic test stand so they can put a maintenance stand on if they wanted to put hydraulic pressure through a maintenance stand to the aircraft to check stuff. But more importantly for us, this is our nitrogen pressure for our accumulator. So we can check that pre-charge on that accumulator. Now, you'll find that this thing is typically set at 1000 psi, and I think it says right here, right on the side, it says 1000 psi at 70 degrees Fahrenheit accumulator pre-charge. Keep in mind that's a pre-charge. All right. Once we put that 1000 psi pre-charge in there, and then we fire off the APP, and the second stage hydraulic system comes up to 26 to 3200 psi, our gauge should reflect 3200 or around 3200 psi. That nitrogen pre-charge is just going to guarantee that we keep constant pressure on the reservoir to get the constant head pressure on the pump. If this pressure drops down below that, then we've got a leak in the hydraulic system somewheres, or our nitrogen pressure has bled off. And typically you'll find this is a misunderstood system, because a lot of times we'll pre-flight and we think that we just need to have 1000 psi on this gauge. That gauge should actually read system pressure for the most part, depending on outside air temperature. All right. Sliding back, this is a good example to look at those switches. So looking at our main rotor servos, our forward main rotor servo, 2 halves, so you can kind of see where it's split. So you can kind of see where the servos kind of split. Upper half, lower half. Lower half is pressurized by first stage hydraulic system at 3000 psi. Upper half is serviced by second stage hydraulic system at 3000 psi. Now here's your pressure switch. So right here is your pressure switch. It's going to cause us to get the second stage main rotor servo bypass caution light when the pitch locks first advance. When that pressure drops below 3000 psi because the isolation valve closed, it's now down below 2000. This is the switch that's going to sense that and give us our caution light. It's also the same switch that's going to sense that in normal flight, when we have 3000 available, if something's happening in this servo and it's going into a bypass mode, if we're having some kind of an internal failure with the servo, that's the switch that's going to give us our caution light. First stage has the same setup. On the bottom side of the first stage section of the servo, we've got the same switch. So you can see here we've got the cannon plug disconnected to it, but right there is your same switch for first stage. You control that. Flight controls coming in. Good things I like to look at on these flight controls, as you can see, we're loose here, but typically you check those. You can kind of roll the flight control around, check your rod ends. You just want to check them for play. And the other thing I like to look at is you see your rivets that are attaching your rod end to your actual control rod. You can tell if these things are getting worn by just looking at right where the washer is to that rivet. If you see a little line of black grease, almost like somebody took a pencil and drew a line around that, you can almost guarantee that if you grab this and do this, you'll see that grease line start to expand and contract. That tells you you've got a working rivets loose. You want to pay attention to those when you're pre-flighting. So you can kind of check each one of those, kind of move them around. You can also, as you roll them around, you're looking to feel for roughness, grittiness in there. All right. Now, one thing with the 53, the roll channel, you always have a little bit of play in your roll channel. So when you come up and you move it, don't be alarmed that, hey, I can move my roll channel like this. There's always a little bit of what we call hysteresis, slop in the roll channel. It's there. Underneath each one of your main rotor servos, you've got a centering spring. All right, so centering spring here, another centering spring sitting down here, and another one for your aft servo on the other side. Again, forward main rotor servo, lateral main rotor servo. So if we think of that old law of gyroscopics, if we make an input to an advancing component, that input is going to react 90 degrees in front of where we put the input in. So this servo, if we make an input to this servo, we're going to get a reaction right at the nose of the aircraft, which is in our pitch channel. So this is pretty much, our forward servo is pretty much our pitch main rotor servo, forward and aft. Lateral, if we make an input here to our lateral, good old gyroscopic precession, 90 degrees forward of our advancing blade, we're going to get the input. So this is going to give us our roll. Our aft servo is pretty much dubbed the collective. So if we pull up on our collective, we're also going to get input from the other two servos moving up and down. Now, to kind of counterbalance out, because we've only got 3 servos, we've got these big old things called stationary scissors on the front side, the main gearbox port side. So our stationary scissors sit over there. They just kind of act as another set of balancing, so that as our swash plate is moving up and down on the shaft of the main gearbox, the output shaft of the main gearbox, it's smooth, it doesn't bind. Right? And then there's our spherical bearing right here. And then of course our swash plates rotating on the outside, and you can kind of see that line right there. It separates your rotating and stationary. So from here out, you're rotating. From here in, stationary. So as you can see, servos, scissors, everything attached to your stationary swash plate. So as it pushes up, pulls down, tilts it on the bearing, your rotating swash plate is going to be able to make those reactions through the pitch control rods to our flight control, to our blades. Back to our centering springs. As we're looking at our centering springs, we have shear pins. The shear pin is just simply to tell us if this centering spring were to jam. So normal flight, as my controls are moving in and out, so is the piston on my centering spring. It's going to push, pull. It's under tension with a big coil spring in here that should my flight control be sheared somewhere forward of that, then that's going to put my controls at a somewhat neutral detent for that said servo. All right. However, just like anything else, if it's mechanical, it can jam. So if this spring in here were to get rusty, corroded, or just, heaven's sake, is misadjusted and jammed, this shear pin here is going to shear so that we don't have binding controls. So as we move our controls, if this piston doesn't extend and retract, as the bell crank moves, it's going to simply just push the arm back and break that shear pin off. So as we look at that on pre-flight, we'll always want to make sure that both halves are in and it's a solid rod. We can't push or pull on it. And that's each one of our main rotor servos. Moving back aft into the aft hydraulics compartment, we can see the aft face or aft side of the main gearbox. Oil filter, got 2 buttons that's going to pop out. One's red, one's yellow. Red is we are in bypass, yellow is it's impending bypass. Either one of those, if we see the button popped out, it's going to say something to maintenance control. Let them come out here and do the business, what they've got to do. Directly below that is our drive shaft to our main gearbox oil cooler. And below that is our heat exchanger for the Utility 2 hydraulic system. Kind of stuck back here. It was an afterthought, as the aircraft was originally a CH that was morphed over to become the MH, so they had to find a spot for that U2 system. And then sitting inside, so if we had our cowling closed or our access panel closed, as we open the door, sitting here on this aft bulkhead is our pitch lock control valve. So as you can see, we can actually engage and disengage pitch locks through doing this. Not something that we practice. This is only our maintenance guys. If maintenance control dictates that, hey, we've got a problem with pitch locks and they need to get the aircraft folded, they can direct through QA to utilize that pitch lock control valve. And then directly behind that, it's going to be difficult to see, but if you use your step as a reference, if you notice here in your lower step, there's a couple bolts right here. On the back side, what is attached to that is your safety valve. So right here, where I've got my light shining, is your safety valve. And I don't know if you're able to capture that, if you can get in close enough to see that or not. Awesome. So, safety valve, the key with that is anything that's going to happen, blade fold, pylon fold, or rotor positioning, safety valve has to open. Safety valve, just like many other things on the aircraft, is controlled by our weight on wheels switch. So, we're not going to be able to open the safety valve in flight. Once we're weight on wheels, we're on the deck. Then through using the master power switch, we can open up the safety valve, allow hydraulic pressure to come through to components such as our pitch lock control valve, to our blade fold, to our pylon, and to our rotor positioner. Now, if we're positioning the rotor head for engine start, we use the rotor positioner for engine start. It's still going to open up the safety valve. We just don't have to reach over and hit the master power switch. It does it for us. It's smart enough to know that, hey, if I want a rotor or want a position for engine start, I've got to open up the safety valve, get pressure to my position. There's a little thing I think in the NATOS tells us if we hold that for too long after it's in position, then the safety valve may stick in the open position. In order for us to clear that, we just have to go back over and cycle master power switch on the blade pylon fold control panel on and off, and it'll clear that safety valve open line. It'll go back to a closed state. That'll probably happen to you a few times. It may have already happened to you. All right. Inside, and we'll come up over the top and kind of look down, we'll see that position. We'll see where we've got the position and everything. And I don't know if you can kind of lean on it. So when we talk about positioner, everything sits back on the back side of this main gearbox, way down here on the porch side. Extremely hard to see when we've got all of our cowlings installed, everything's ready for flight, but the easiest way you can probably look at it is to come through from the main gearbox oil cooler compartment and kind of look across. In flight, that's the best shot you're going to get at it. And then the other way is to kind of look up underneath the eaves, the number 2 eaves. So sitting here, yeah, it's different. So sitting here is my actual, this is my positioner. And if I look at my rotor brake disc, I see the teeth in my rotor brake disc. My positioner has a little cog wheel that's going to come out. It engages with the teeth in that disc, and that's what's going to rotate my main rotor and tail rotor head to put myself in position for blade fold, pylon fold, or for engine start. To the side of that is the actual hydraulic motor that's directing the fluid to the positioner. So there's my hydraulic motor. And then back, way back in this corner, I don't know if I can get a light on it, is my actual, what I call positioning and reversing valves. These are receiving a signal from our slip ring that tells us whether or not we want to go in a clockwise direction or counterclockwise direction. What is the fastest way to get the rotor head into the position that you want? Now, I don't remember off the top of my head, but I believe engine start will only go one direction, whereas blade fold, pylon fold, it'll select whether it wants to go forward or reverse. But I believe engine start only goes in a counterclockwise fashion. And I'll have to research an ATOS for sure. Above that, we've got our NG TAC generator pad. We've actually got our generator there for the number 2 engine. And we've got our NF flex shaft for number 2 engine. Then of course on this engine accessory section, we have our gimbal assembly. You can see your torque sensor shaft and housing coming in and making contact. So torque sensor shaft and housing coming in and making contact with the gimbal assembly. All right, rotor brake. So sitting right here on our tail rotor takeoff flange on the back side of the main gearbox is our rotor brake disc. Surrounding the disc is our actual rotor brake itself. All right. Directly below that, it's going to be hard to see, but directly below that is our Gust lock. extends down through into the cabin overhead, and we'll look at that when we go down inside. We'll look at the gust lock handle. We'll see how that extends up. It's got a tooth that's going to engage in between the disc and mechanically lock our rotor system so that we don't have to worry about it when we shut down. Coming back over into the compartment where you're at, we're going to look at the actual rotor brake, and we'll probably slide back in there and we'll look at the manifold and everything. So our rotor brake assembly, independent system. It's not pressurized by utility 1, second stage, or anything like that. It's an independent system. Manifold sits right here. Manifold has a reservoir. We can check the servicing by looking at the sight gauge on the side of it. And then with the reservoir, there's a dump valve right on the back side here that we can push down. That dump valve is also connected with a cable to our manual release handle in the cabin overhead. Now here on the trainer, that manual release handle sits right here. But if reference point for the cabin, if we're in the cabin overhead and we walk aft on the starboard side, we come to that first removable, or the only removable window on the starboard side, go to the aft frame, slide our hand up the aft frame, go up over the heater ducting, and sitting right there is the manual release handle. So we just trace that framework out, stick our hand up, we can grab that manual release handle and pull it down. All right. Located on the manifold is 2 pressure switches. So right here is 2 pressure switches. The upper pressure switch is our 10 psi. This is going to give us our rotor brake pressure light or caution light in the cockpit. Anytime we have pressure in the system that's 10 psi or above, this pressure switch is going to signify that. The bottom one is our 975 plus or minus 25 psi. That's going to give us our rotor brake on advisory light, or our hard brake or emergency brake, if you want to refer to it as that. Inside here is a 3rd pressure switch. And this pressure switch is our 40 psi pressure switch. Now the 40 psi is for rotor positioning. We have the emergency rotor brake on, so the system is 975 plus or minus 25 psi. We turn master power on and we select blade fold position. When we select blade fold position, the rotor brake is going to dump, so we'll lose our rotor brake pressure light. It's going to repump back to 40 psi, so we'll get the pressure light back on, and it's going to stay there at that 40 psi until we get the head in position. Once the head gets in position, then it's going to repressurize back up to 975 psi. All right. We've got one more pressure switch associated with the rotor brake, and we call it our soft rotor brake pressure, or the 350 plus or minus 35 psi. If you look through here, I believe looking through here, you should be able to see, I'll highlight it for you. Right here, and it kind of sits right next to the oil pressure transmitter, your main gearbox, so that this black item right here on the back side, that's your main gearbox oil pressure transmitter. So that's where you're receiving your cockpit readings for your main gearbox oil pressure. This is your 350 plus or minus 35 psi rotor brake pressure switch. This is your soft switch. This comes into play when we're shutting down normal conditions, and we use our rotor brake switch. Spring loaded to the off position, so we pull the switch down, hold it for approximately 5 seconds. It's going to energize the system to 350 psi. Rotor stops. 1 minute after we let go of that switch, the system will repressurize back up to 975 psi. We don't have to do anything. All right, so this is that 350 psi, or our normal rotor brake pressure. You stay right there, we're going to talk about that. So this valve back here on the deck looks identical to the 2nd stage isolation valve. This is your 1st stage isolation valve. Now, 1st stage isolation valve, we don't have to worry. It's not necessarily coming into play when we're doing blade fold, pylon fold, anything like that, because we don't have the 1st stage hydraulic system online until we spin the rotor head, because it pumps on the back side of the main gearbox. But what this is for is our maintenance personnel. We get guys that come out here and want to put a hydraulic test stand on the system when we got pitch locks advanced. This is going to protect them from getting fluid to those main rotor servos. So again, it's related to the pitch locks advanced. Whenever the first pitch lock advances, this isolation valve closes, as well as the 2nd stage. Now, we don't see any difference in the cockpit because we already had the first stage main rotor servo bypass caution light on because there was no pressure in the system. But it's closed. It will not reopen until the pitch locks are disengaged and the advanced light goes out. Now, if they wanted to put a hydraulic test stand on the system, they can put it on and they can run the first stage system up with a ground test stand. So this is what this is for. Good shot back at the back side of your main gearbox. We can look back and see. I'll let you get in here. We can look back in and see. You see the number 2 generator. So you peek at the number 2 generator. Right below that, we got our NR TAC generator. And then right here to the side, we got our first stage hydraulic pump. Sits on the back side of that main gearbox. All right, so keeping with the first stage hydraulic system, in the main gearbox oil cooler compartment, right here on the deck in front of the main gearbox oil cooler, we have our fin tube heat exchanger for the first stage. 2 sections, one section here in this main gearbox oil cooler compartment, the other section runs up the tail pylon. All right, so that'll help to cool off our first stage hydraulic system. On the bulkhead, just underneath this drive shaft, is where we have our pressure manifold. Just like the second stage pressure manifold, if we come back around the front side, we will see that we've got a pressure switch. So we've got the front side, we've got a pressure switch. Right here. I don't know if you can see that. But we've got a pressure switch right there. And then we've got the solenoid for the shutoff valve. So it looks almost identical to the second stage in that sense. So pressure manifold, filter, solenoid for the shutoff valve. Right below that solenoid for the shutoff valve is where our system pressure switch is at. It's going to give us our caution light in the cockpit if we go below 2,000 psi. Return filter sits here. And then, of course, our reservoir and our accumulator again. Nitrogen pressure gauge for our accumulator sits right here in the compartment. And again, you can see the reading where it says 1,000 psi at 70 degrees Fahrenheit gas pre-charge. That's pre-charge once the system is operated. So once we release the rotor brake and bring the rotor head online, that first stage hydraulic pump comes into play. Our system gauge should come up to around 26 to 3,200 psi, depending on outside air temp. Shouldn't drop below that unless we've got a leak in the system or we've lost nitrogen pressure. There's really no way to know whether it's a leak or loss of nitrogen pressure other than to come up here and let the pressure out. So if we look at the gauge and it looks like it's only 1,500 psi, we don't know if that's truly just a loss of hydraulic fluid because we've got a leak in the system somewhere, or have we got low nitrogen pressure. We've got maintenance procedures to bleed that off to find out what it is. We can kind of crack some lines back here, bleed off the hydraulic fluid, and see where the nitrogen is really reading. In most cases, the nitrogen is low, more than anything else. All right, main gearbox oil cooler, pretty simple. Sitting in this upper cowling is our detector for our Ibis system. So it'll detect anytime one of the main rotor blades comes around. If we've got one of those popped indicators, the detector is going to pick that up and send a signal down into the signal processor in the cabin overhead. So we'll look at, I think we've got a blade over here in the corner that actually has an indicator on it, and it has this sense of a popped indicator. All right, we'll move down. Unless, we need to do a rotor head too, but we can do that. You want to do that now?
Yeah, that'd be great.
So let's look at the rotor head. Start at the top and we'll work our way down. So blade fold junction box, this is what's receiving that electrical signal from the slip ring. So when we go to the cabin, we'll look down the bottom, see the slip ring at the base of the main gearbox shaft. That takes the stationary electrical, turns it rotating, brings it up through the shaft of the main gearbox and brings it out here and allows it to continue to spin around. Electrical inputs going out to each one of our sleeve and spindles. within the center of that blade fold junction box is where our damper accumulator pin is at. And you got your servicing indications here, and you also have your NATOS procedures on checking that to see where the pin should be. Pin is going to indicate whether or not I need hydraulic fluid in my damper system. As far as nitrogen goes, I find the number one blade, locate the number one blade, and I can find my nitrogen gauge for my damper accumulator out here. So I can look at that and see if it's within the right pre-charge for my outside air temperature. Coming out, main rotor hub, the wagon wheel if you will, and on that number one arm of the main rotor hub is my blade fold control valve. And you can see we have the same setup as our pitch lock valve. I can push here. Not a practice that we've ever done or will ever do is to come up here and fold the blades using this blade fold control valve. Let the system do itself from there. Surrounding the hub, center of the hub, is our blade fold manifold. All these hydraulic lines is our blade fold manifold going off to the individual blades. So we'll choose one of the blades, come out through to this sleeve and spindle, and you notice the difference. This sleeve and spindle as compared to number one sleeve and spindle. The number one sleeve and spindle hinge is bolted in place, and it doesn't have any blade fold components. No pitch lock, no blade fold. All right, come out to this sleeve and spindle. We've got one pitch lock per blades that do fold, number 2 through 7. So we've got 6 pitch locks on the aircraft. One pitch lock is going to lock my sleeve and spindle into a somewhat neutral pitch for that blade, for blade fold. So we've got all of our blades that are going to fold in a somewhat of a flat pitch. And it's going to come through the receiver on the back side. Once the pitch lock engages through the receiver, that's going to hit a sequence valve, and that's kind of our timing, if you will. Once it hits this sequence valve, it says, okay, now any fluid coming through to this sleeve and spindle can go to the next component in line for blade fold. So first, fluid's got to get to the pitch lock's got to engage with the receiver, sequence valve is going to open up the path for the fluid to come up through, and from there it's going to go to my blade locks. All right. On my blade locks, 2 blade locks per sleeve and spindle that folds, so I look at 12 blade locks. I've got lock pin locks. So hydraulic fluid would then tell my lock pin locks to retract. Then my blade locks can retract. Once my blade locks retract, then the fluid is going to be directed to my fold cylinder, which is internal in my sleeve and spindle. If I look in here in the opening, I can kind of see the linkage. That's all I'm going to be able to see is the linkage. And then down in here, let's see if I can get my light on that, we can see the rod end to that piston, but we don't actually see the piston. So you can kind of see right there is the rod end, the fold cylinder, right there. And the actual cylinder itself is back internally inside. Once the blade folds around, it's got a receiver, if you will. It's going to make contact with a micro switch. All right. So once all of my blades come around and make contact, all 6 blades that fold will make contact with a micro switch. I will get my blades folded light in the cockpit. All right. Reverse this, come back to spread cycle. Fold cylinder is going to extend the sleeve and spindle around. Hinge is going to come through and make contact. Now, if you notice these big push rods, they're spring loaded. They're going to extend out. So as my hinge comes through, it's going to make contact. It pushes these rods back. We've got another sequence valve. So now hydraulic fluid that was going to this fold cylinder that just spread my blade is now going to make contact with this sequence valve, and it says, okay, now direct hydraulic fluid to my blade locks. Blade locks are going to engage. Lock pin locks engage. And as you can see, each one of these have a micro switch. This is what's going to control my blade spread light. Once all of the lock pins have fully engaged, all 12, and the lock pin locks are in, then I'm going to get my blade spread light in the cockpit. If I don't have a blade spread light in the cockpit, I can come up here and look at the individual sleeve and spindles and look at the lock pin locks and see, by looking at this screw, there's a little thin painted section right there, and you can just barely see the red line on this one. All right. You would look at that and you see just a little red line ringing around there. That tells you that it's fully engaged. If you see more red than just like somebody took a pencil and drew a line around it, your lock pin locks didn't fully engage, and that's going to be your sleeve and spindle. It's giving you a problem that you don't get a blade spread light. Once you get the blade spread light, now hydraulic pressure is available to your pitch locks to retract your pitch locks. And again, your pitch locks advanced and pitch locks engaged are being controlled by these micro switches here. So one up top, one on the bottom. And if these are clearly marked, I think they're probably all damaged, but if you look on the aircraft, you'll be able to see one of them will tell you advanced, one will be able to say, or one says lock and the other one just says advance. So you'll know which one is giving you your advanced light, which one's giving you your pitch lock light. All right, coming down, dampers, one for each blade. Hydraulic pressure is being supplied by the accumulator, which sits down in the cavity of the main gearbox shaft with its pin sticking up to tell us hydraulic servicing. Each damper is going to position those blades back to their full lag position on shutdown. It's going to help us with blade force and keep our blades spread at a set distance from one another. It also absorbs the startup and shutdown shock when we engage the rotor, disengage the rotor. This is going to be our shock absorber, if you will. And then it allows our blade to do some hunting in flight for a little bit better flight performance. Swing around. Pitch control rods. Things we're looking for here, you want to watch for, you got rotating scissors. So a good way to check that is you can grab a hold of your horn, or you can grab your pitch control rods and you just kind of try to rotate your head back and forth. See if you got any kind of play in your rotating scissors. Watch your linkage, your bolts and stuff like that, see if you see anything moving around. And then same deal with your pitch control rods like we did with our flight controls. You want to make sure that they're smooth, and then you can try to move those. You can try to pop them up and down, try to slide them in and out. See if you got any kind of play, if anything feels loose in there. All right. Flap restrainers, and then your droop stops. This is the key thing that's going to cause you to drop a blade. All right. This is a pretty good aircraft as far as safety features. Everything's set up to make sure, like we said, sequencing and stuff for blade fold. But if when you pre-flight, we have a nasty little habit sometimes of grabbing a flap restrainer and letting it go like that. We get out there, we work in an environment that's salty, it's grimy, nasty. We get stuff up in there, we might grab it, it might hit and come back out and stick right there. If this flap restrainer is not fully in and engaged, then when we go to blade fold, we're going to drop a blade on the deck. And this is the only thing that's going to cause us to drop a blade on the deck. So we know we're going to do blade fold, we want to make sure that we push these, grab them, and push them all the way back in. Then of course our droop stops, we can look at our little Pac-Man, make sure that they're clean and stuff. We're up here pre-flighting, we know we're going to spin up the crewman, we're going to be looking at that to tell you when flap restrainers or when your droop stops are out. And then again when shutdown, when the droop stops go back in. So we'll pick up on our gust lock. Now our gust lock, as you can see, extends through the overhead. That goes right up to that rubber boot that we saw earlier that was just below the rotor brake disc, a little bit onto the port side. So handle, you can see the linkage there that's controlling that one tooth that's going to engage with our disc. And then we got some micro switches here that's going to control lights in the cockpit. One of them's going to illuminate our rotor lock light. The other one's going to extinguish the rotor lock light. Now, the key with this for us is if when we're getting ready to go fly, we're always looking for that blade spread flight ready. Well, guess what controls our flight ready? We get the aircraft fully spread out. We don't have a blades folded light. We get the blade spread light. We don't have safety valve open light. Everything's off, but we can't figure out why we don't have a flight ready light. Flight ready light's not on because our rotor is still locked. So if it takes us to unlocked, when the rotor lock caution light goes out, we get our flight ready light. Little thing that catches us every now and then. All right, moving forward, right underneath the main gearbox base, here's that slip ring assembly that we talked about that took all of our stationary electrical, allowed it to become rotating, let it spin as it went up through the rotor system or through the center of the shaft and come out at the top to that blade fold junction box. In the center of our slip ring is the rotary coupling. It does the same thing with our hydraulic fluid. It needs to get out to those individual blades. So stationary hydraulic input allows it to go rotating, so it can rotate as it goes up through the shaft and come out at the top and continue to spin and go out to the individual blades. It's a good time as we're here on the bottom side of the main gearbox to kind of look at the bottom side. Our chip detectors, got one chip protector here, and then we should have our second chip protector right over here. This is our aux sump. This is our main sump chip detector. All right. Both of these have 30-second time delay. And what does that mean for us? That means because where they sit and a lot of that oil returning falls down, a lot of junk and garbage may fall on those. So before we even get that main gearbox chip light, if we locate it on the panel to be one of these sensors or detectors, it's already waited 30 seconds before it gave us that chip light. So a lot of guys think that on our chip locator panel, which on our trainer sits here, but in the aircraft just sits on that port cabin wall just after the escape hatch, they think that as I rotate this around and I get to that position for the main sump or the aux sump 4 or 5, that hey, if I rotate it to 4 and I don't have, my light doesn't come on, I gotta wait 30 seconds. Now, the 30 seconds has already happened. When you got your chip light in the cockpit, if it was coming from one of those, it already waited 30 seconds. So I come over here, if that light's on, it's no kidding, the main sump has got some stuff on it. And the same thing, go to aux sump. Again, 6 is not used, it's just an additional position, maybe for future growth of the gearbox, if you will. It's not used, so five positions we can select from and check. All right, coming forward, we talked about, up top, we talked about the mixing unit and how we picked up our sense for our collective. This is, we call it the collective bias block, but this is where we're getting that load signaling to hold desired NF. So as we move the collective stick, this is going to pull on the respective engine going out to the fuel control unit. So if you want, I'm going to pull on the collective and see if I can make that move at all so you can see the correlation.
Mind if I hold the light?
That's what it is. Let's see if we can make that move around. I don't know if that translates to a whole lot of movement.
No, you can't really see it.
But that's our collective bias. When we talk about having to adjust collective bias, that's what we're talking about. All right. Moving in front of that, with these little things called engine tensioners. These engine tensioners are going to tell us where our speed control levers are. They do some good things for us. One of the first things that we'll talk about is the rotor brake. All right. So if I'm engaged in rotor brake, we talked about earlier that if I put the soft brake on, I hold the switch, I hold that rotor brake switch for 5 seconds, or approximately 5 seconds, then it's going to automatically re-engage to 975. But what we didn't talk about is when can we put that switch on. All right, so the criteria is that my speed control levers in the cockpit, I need to have at least 2 of these at shut off, third one, at least 2 of these at shut off, third one at ground idle. So as I'm moving these around, my cable tensioners are going to sense where my speed control levers are. So when I'm getting ready to use my rotor brake, if I've got 2 of them at shut off and my third one's at ground idle or below, then I can engage my rotor brake. If I don't have that, those are what should be stopping me from doing damage to myself, i.e. engaging the rotor brake when the rotor system's not ready for it. They're also what we use for blade fold. One of our things for blade fold is we have to have all 3 speed control levers at shut off. Those tensioners are going to sense that when all 3 speed control levers are shut off. If not, it's not going to let us fold the blades. 1 for each engine. They sit right there in the cabin overhead. All right. Moving forward, talk about the AFCF servos. And we really probably should go and get a cabin one day and just go through the aircraft cabin, actual location where all this stuff's at. We can point it out and look at it. So, looking at our AFCF servos, I like to start at the top, pitch, altitude, roll, yaw. Some people like to go Y-wrap from the bottom up. So yaw, roll, altitude, pitch. But 2 hydraulic systems supplying pressure to this. Second stage on the bottom half, utility 1 hydraulic system on the upper half, and again at 1000 psi. So we'll look at the yaw. If we look at the yaw AFCF servo and we come down, we notice at the bottom of our AFCF servos we got some springs called balance springs, but we don't have a balance spring on our yaw. Just because where the rudder pedals sit, there's no need for it. The balance springs are doing exactly what they say. They're balancing our flight controls. So when I leave the stick, centered as it is now, the balance spring's what's holding the stick in that position. So if I have a problem with my flight controls and my cyclic stick, I let go of my cyclic stick and it wants to fall left, right, fore, or aft, I got something going on with balance spring. I need to let the maintenance guys know and they can take care of it. Again, the yaw channel, because of the nature of where the pedals sit, they're not going to fall very far. So there's no need for a balance spring on those. The other thing that's different is if we come over and look at the roll channel, we notice as we come up on the input of the roll channel from the balance spring, we notice we get an assembly that's called a roll damper. All right. The yaw channel doesn't have any damper, external damper. All of its dampening action is done internally within inside of the servo itself. The roll channel has a damper here that's external on the input side, and all it is just a little valve or a flapper, if you will, paddle inside that box. As that paddle rotates back and forth, the fluid inside there must go from one side of the paddle to the other. Inside the center of that paddle is a little tiny orifice. The fluid can only get through the orifice at a certain rate, so that's going to help to restrict or control the movement of that roll channel in an effort to try to minimize pilot-induced oscillations. And if we come over to the collective has a damper as well, just not in this AFCS compartment. The collective damper is in the port eBay, so we'll look at that. We'll go out and take a look at that and show you where it's at. The pitch has its dampening action through this item above the top called the fast actuator, force augmentation system. All right, this force augmentation system with a fast actuator is pressurized by whichever system is supplying pressure to the AFCF servo. So if it's utility 1 supplying pressure, utility 1 is going to pressurize the fast actuator. If second stage is supplying pressure to your AFCF servos, second stage is supplying pressure to your fast actuator. There's an input rod to the fast actuator right here that has a shear pin. We like to look at that on pre-flight. So easiest way for us to check that on pre-flight is if I slide my hand in and I get the back side, I hold this control rod, because we typically have a linkage here. There'll be a rod end that extends down here from this actuator and hooks in. And then if I come to the input side and I find my input rod coming in and I follow my hand up the input rod, I'm going to find one bolt and then I'll come right above and find the second bolt. So I'm just going to kind of put my hand on it, let myself slide up. I'll find one bolt, and I find the second bolt, and then I can rotate. So then what I'll do is at the top, I want to hold that rod end stationary at the top, and at the bottom I want to try to rotate. If I can rotate that, then I've got a sheared, my fast actuator rod has got a sheared pin. If I can't, it's stationary as it is here, everything's good to go. All right, let's take a look at the eBay and show you where that damper's at, that collective dampers. Oh, you know what? We may not have it sitting there. Nope. So we were definitely going to have to go out. Your collective damper would sit. If you look into your port eBay, you open up your port eBay and you look into the shelf, you would see that same little green box or gray box that you had under the roll sitting underneath the shelf right next to your collective inputs or collective controls. And then you can see how it attaches. I do want to go over to the other side though, and I want to show you the collective detent for blade fold. So in your starboard eBay, and this is hard to see on the aircraft with the refueling probe in place, but once you open up that starboard eBay and you see your refueling probe, if you look up underneath to the back of the fueling probe, you'll see your torque shaft that comes through from the co-pilot's collective, pilot's collective, all the way through to your inputs going to your AFCF servo. On that collective side, you've got what's called a collective detent. And here we can see it's just a little roller plunger is all it is. And if you look on the inboard side of that, you'll be able to see there's a little V right here that this roller is going to roll into. And I don't know if you can catch it from this angle down in there, but you can see that little plunger that sits, my hand in there, see that little plunger right there? And there's a little V groove right there in that wheel. So as we move the collective, that plunger will ride, and when it drops into that V groove, that's going to open up, or it's going to eliminate our stick position indicator here on the instrument pad. Once our stick position indicator illuminates, then It's going to give us our indication of whether we need to move our cyclic stick fore and aft, left and right. And you know what? While we're up there at the mixing unit, guess what we didn't look at? We didn't look at those sensors, those stick position sensors. But right on the back side of the mixing unit, you got two little goldish green boxes. And you find them by looking at the little control rods that come from the boxes back to the aft shaft on the mixing unit. The outboard one is your pitch, inboard one is your roll. So as I move my cyclic stick, those are the sensors that's going to tell me whether I need to move fore and aft on my pitch, left and right on my cyclic stick. And then once I get myself in position to engage pitch locks, my center segment on my stick position indicator will go all illuminated, it'll be a little square, and then each one of the corners will illuminate, and that tells me I'm in position for pitch locks. I can hold my controls, and I can put my switch to the pitch lock position. Again, when the first pitch lock advances, I will get pitch lock advance light, and then I'll get a second stage main or a servo bypass light. Transition section, tail pylon section. We can see, which is nice, it's folded. We can see our blade or our pylon fold components back here. Pylon lock pin cylinders, just like our blade lock pin cylinders, just a little bit bigger because we've got to hold that big old pylon in position. And as you can see, your pylon lock pin cylinders are mechanically linked through to your tail rotor disconnect coupling. And on the back side of your disconnect coupling, you have a little thing called a yoke assembly. Right here. I don't know if you can catch that, but right back there is the yoke assembly. This is what is engaging and disengaging your disconnect coupling when we fold the pylon, all right? And it's doing it through this linkage going all the way back up through, all right? So it's being triggered by your lock pin cylinders. Your lock pin cylinders, there's a sequence valve out here, all right? So as your lock pin cylinders come into play and they drive, the lock pin cylinders come out and withdraw, they're going to hit your sequence valve and say, okay, now hydraulic fluid can go through to my pylon fold cylinders. Two big pylon fold cylinders, one fold cylinder in the pylon section and one fold cylinder in the transition section, or in the one in the transition section, one in the pylon section. Some folded around. Same deal when we come back to spread, hydraulic fluids come into our cylinders. As the pylon comes around, there's a striker plate that's going to make contact with another sequence valve. We nickname this sometimes the bayonet switch. So you may hear some people say we had a problem with the bayonet switch. This is the sequence valve that they're talking about when they say the bayonet switch. So as that striker plate makes contact, it's going to push in on it and says, okay, I have come to a spread position. I'm now ready to engage my lock pin cylinders. Now the hydraulic fluid will be directed to your lock pin cylinders. As your lock pin cylinders engage, the yoke assembly is going to engage your coupling, your disconnect coupling. It's going to re-engage your disconnect coupling. We've got some flags. One flag that strictly indicates your disconnect coupling, so you can see up here where it's riding. There's a little tooth right there on the back side that's going to ride that disconnect coupling. So when the coupling comes back in and re-engages, it's going to push that tooth in. As the tooth gets pushed in, it's going to pull your flag up out of position. All right. Same deal when it comes out. So we can look at this. It's a good indicator for us. If we think we've got something going on with the pylon, we can look back and see if there's any flags down. On the side, your lock pin locks or your pylon locks have flags also to give us a visual indication. So as we walk around, we can see whether or not our lock pins have fully engaged. Flags will be up, not visible, out of sight. And if we look over here to travel this back through, you can see our tail skid, electrical actuator. Get that disconnected, but tail skid, electrical actuator. Nothing more than just a strut, hydraulic and nitrogen. So it's got nitrogen servicing here, hydraulic servicing on the top side up here. And then it's got an electrical actuator that's going to allow the tail skid to extend and retract with the landing gear in flight. And again, through the weight on wheel switch, extend and retract with our ramp on the ground on the flight deck. Here's that second section of the fin tube heat exchanger for the first stage hydraulic system that runs up the tail pylon. And then your number 7 drive shaft, number 7 tail drive shaft coming out of the IGB going up through to your tail gearbox. And then tail gearbox, you can get a good shot of your chip detector. And the unique thing with this chip detector and the chip detector on your IGB, you should see, I think it's on your side. Would be right in here somewhere. Right here, it just got it broke off. This is your chip detector for your IGB. The IGB and the tail gearbox are dual purpose. The chip detectors also sense temperature. So if you're getting a tail gearbox chip or you're getting an IGB chip, you got a 50-50 chance that it's hot oil versus a chip. You won't really know until you get it shut down. They pull it out and look at it and see whether or not there's anything on the detector. Tail rotor head, pitch change links, and just like our main rotor heads, the tail rotor blades also have flap restrainers. So right back here, we've got a flap restrainer. It's going to allow our blades to flap in flight. Not as much movement as the main rotor blades have, but it is give us a little bit of movement. When we slow RPMs and come to shutdown, they should re-engage to limit that banging around out on the flight line with windy conditions, stuff to that nature. On the back side, on this housing of the tail gearbox, we have the tail rotor positioning actuator. Electrical motor, tail rotor positioning actuator. The way it works is anytime I want to fold the pylon, whether I've already got the head folded or I'm going to go ahead and fold the pylon by itself with the head spread, the actuator is going to come out and it's going to engage with this cam, the tail rotor positioning cam. So the actuator would extend out, it's going to make contact with the cam, and it's going to stop. It's going to stop and wait for my pylon, for my disconnect coupling to discouple, wait for my lock pin locks to retract. Once that happens, then it's going to send a signal back here and it's going to say fully extend. When it fully extends, it's going to rotate all the way around until this actuator can get it into the bottom groove of this cam. We call it the valley. All right. Once it extends in the valley of the cam, you can see it puts our tail rotor blades at kind of that crisscross pattern. Sets us up so that we're not going to make contact with the main rotor blades, whether it's folded or the blades are spread. When we come back to the spread cycle, we're not going to get rid of our pylon unsafe for flight light until this actuator fully retracts. It's the last item on our pylon fold side that's going to retract. It may take a couple seconds. You feel the pylon come around, you feel that lunky clunk clunk, you hear the lock pins drive in, but you're not going to get rid of the pylon unsafe for flight light until this fully retracts. So just be patient with it. And if it seems like it's taking too long, you can have your crewman take a peek up there and look and see if that actuator is retracted. Out on the front side, we got a pitch change shaft. You can kind of see it in here. But you got a pitch change shaft right here that extends all the way back through this housing, this tail gearbox housing, all the way back to this tail rotor servo right here. As this tail rotor servo, as you can see, as this tail rotor servo extends or retracts through movement or rudder pedals, it's going to cause movement of my pitch beam. As my pitch beam moves, pushes or pulls, it's going to pull on my pitch links and help change the pitch of my tail rotor blades. All right. So pitch beam support, like some people will call it, they'll nickname it the milk stool. But pitch beam support's just sitting up there. Pitch beam, pitch change shaft, right here, pitch change shaft, and then my individual pitch change links. Individual pitch change links. Alright, so now we'll look at the engine, T64 GE419 turbo shaft engine. And I think we advertised that it puts out, what's it, 4,280 shaft horsepower at 137% torque. Got a contingency of 5,000 shaft horsepower for 2 minutes. So a beast of a monster. 5 sections. First section we're going to talk about is the front frame section. All right, so from this band to right here is our front frame section. Next section that we'll talk about will be our compressor section. Picks up from right here, and our compressor section runs all the way back aft to right here. You can kind of see the band right here. And then our next section after the compressor section is our combustion section. It comes from here all the way back to right here. And then we have our turbine section. Turbine section has 2 turbines in it. First one is our gas generator turbine, and then our free turbine. And then our exhaust section. is our last section. So we'll come back and we'll talk about this front frame section. What do we have on the front frame section? First, we have this fuel oil heat exchanger. All it's doing is it's using the cool fuel from our tanks to kind of dissipate the heat in that hot oil, returning back through from the engine back through to the sump. So just dissipating hot oils using the cool fuel from our engine tanks to dissipate the hot oil that's returning back through from our engine. Come below, right here at the 6 o'clock, mounted at the 6 o'clock section, is our engine accessory drive gearbox. Engine accessory drive gearbox. Front side of the engine accessory drive gearbox has two components. First one is our fuel boost pump. Next one is an NG tack generator. All right. NG tack generator and our fuel boost pump. Our fuel boost pump is what's going to draw the fuel from the fuel tanks, sends it through our inline fuel filters. We dub these the airframe fuel filters. You'll hear a lot of people say the airframe fuel filters, but our inline fuel filters. From there, it's going to push fuel to the engine-driven fuel pump and filter. And the engine-driven fuel pump and filter is on the back side of our engine accessory drive gearbox. A little difficult to see on this engine, but if you look, it sits right back here. So there's the filter, and there's the engine-driven fuel pump right here. Fuel filter, fuel pump. So from that boost pump and those inline fuel filters, it's going to come to your engine-driven fuel pump and filter to our fuel control. Then it's going to be sent out to our fuel nozzles on the engine. We'll look at those here in just a second. So if we're starting the engine on startup, we need both this engine-driven fuel pump to work and we need our fuel boost pump to work. Once the engine's online, it becomes self-sustaining. If something happens, maybe that filter gets clogged or bypassed, or this boost pump fails, the engine's still self-sustaining as long as the engine-driven fuel pump's up and running. This one can drop off and go away. Typically we want it there, but if it goes away, it's not going to hurt us. On the back side of this engine accessory drive gearbox, we have our hydraulic start motor. It's taking that 4,000 psi from the respective start valve, comes down to the start motor. Through the accessory drive gearbox, it's going to start to drive our compressor, start to spin our compressor, so we can compress that incoming air and then shoot it back through to a combustion section. Directly below that is our lube pump and filter. So lube pump and filter for the engine. And then on the other side, and we'll go over and look at a number 2 engine, but right here, way back up in there, is the fuel control. So way back in there, and we'll get a better shot number 2 engine or number 1 engine. You actually can see it. You can see what it looks like is our fuel control unit. All right. Also mounted on our front frame on the very top, and we'll look again at number 2 engine, we've got an anti-ice valve. Using air from our compressor section, we use that hot air, bleed air from the compressor section. It comes back and it's going to anti-ice 5 of our 6 struts on our front frame. The bottom 6 o'clock position strut on our front frame, as you can see, being attached to the engine accessory drive gearbox, it's going to get anti-ice by hot oil. The other 5 are going to be anti-ice by bleed air coming through from your anti-ice valve. We'll go in the classroom, look at the cutaway, and you'll actually be able to see that. That anti-ice, as it comes through the front frame, will also, because those struts have journaling in them, it's going to supply hot air to the inlet guide vane and keep the inlet guide vane anti-iced on each engine as well. Now on number 1 and number 3, we use bleed air to do a couple other things. We use it for fuel probe extension retraction. We also use it for fuel purge. So we'll look on this engine. I'm hoping it's hooked. There you go. So we can see it's hooked up here. This is our quick disconnect for that bleed air that's coming back to be utilized for the fuel probe or for fuel purging. And if we trace that out, it comes around and goes back up, and you can see it sits right there. That's where it's picking it out and pushing it back through. All right, in front of it is your bleed air that's going back up through to your anti-ice valve. So right here, trace that out, it goes all the way back up to your anti-ice valve up here. And again, we'll look at number 2 engine, we'll get a good look at that. All right, compressor section. On our compressor section, we've got variable geometric actuators, or geometry actuators, variable geometry actuators operated by fuel. So the fuel control unit is basically going to tell these how far to extend or retract in order to open up our inlet guide vane and our first 4 stator vanes that are variable. So 1, 2, 3, 4 stator vanes that are variable. Got 14 stage engine, 14 stator vanes, the first 4 variable, and then we got inlet guide vanes. Our inlet guide vanes are also variable. And we'll look at that in the classroom. We'll take a peek at that. So again, this is what's going to make sure that we get the right fuel and air mixture coming into the engine. So as we put more gas into the engine, this thing's going to say, hey, we need to open these up more. Put less gas in the engine, so close them up more. Sort of like the old carburetor on the car. Back here on the compressor section, we have an ignition unit, exciter control. This is going to supply our electrical power to our 2 ignition plugs, or 2 spark plugs, if you will. So if we trace that back out, we'll find that there's one, we've got one igniter plug right here at roughly the 8 o'clock position. 4 o'clock here, and then another one on the other side over here at 8 o'clock position. All right, so if we trace that back out to my ignition unit, that's my two spark plugs, if you will, or igniters. Fuel flow divider. Our fuel flow divider is taking that fuel coming off from our fuel pump, our engine fuel pump. It's going to divide it and split it and send it off to 6 fuel nozzles on one side, 6 fuel nozzles on the other side. It also has a primary and a secondary port. I think the NATOPS tells us that at 210 psi our secondary port will open up and it'll supply pressure to our secondary fuel nozzle. So if we look at our fuel nozzles, each one of our fuel nozzles, you can kind of see that there's a primary and a secondary. So normally we're putting gas through just one side of this fuel nozzle until we hit 210 psi, and then it's dumping massive gas through both. All right, and this is happening by this fuel flow divider right here. And if you can trace, you can kind of follow your lines back through. And you can see where it splits it, brings it back off to your primary and your secondary fuel nozzle. All right, combustion section. We've got our fuel going in, we've got our ignition going in, and then it drives it back through to our turbine section. Using that heat energy coming back through, gas generator turbine is physically connected to our compressor, all right, because it is one. So as our gas generator turbine spins, it's going to spin our compressor. Once the gas generator turbine gets the compressor spinning at a faster rate than what the hydraulic start motor was, a hydraulic start motor is going to drop out. NATOPS, I think, publishes 51 to 58% NG, or hydraulic start motor should drop out. And then we should get ground idle somewhere around, 60.5 to 70%, depending on outside air temperature. All right. And right behind our gas generator turbine is our free power turbine, or free turbine. I like to call it free power turbine because I use the T5 and NF. We have thermocouples on the inlet side of that power turbine. We've got 14 thermocouples. This is what's giving us our T5 reading in the cockpit, telling us our engine temperature. If we look at this from a crewman standpoint, for circuit breakers, it's power turbine inlet temp, PTIT. So if we look on our circuit breaker panels, if we ever try to find the T5 circuit breaker because maybe we have a problem with our gauge, we're going to have to make sure we're asking to check the PTIT for the respective engine. If we ask them to check T5, they may say, I can't find the T5 circuit breaker because it's labeled as PTIT, power turbine inlet temp. All right, exhaust section. On the back side of the exhaust section, we've got a transducer. This transducer is what's going to pick up and register overspeed on the engine, just like the APP, 110%. So it's got a little wheel, it's spinning. We kind of, it's got a little teeth on it. It's going to indicate when we hit 110%. Once it hits 110%, it sends a signal up through. If we trace this out, comes up, transfers it into this electrical harness, drives it over to the other side, down to our fuel control unit. And you're not going to see it here, but when we look at the number 2 engine, there's a solenoid on that fuel control unit that's going to cycle. So senses 110%, sends a signal up through to the solenoid and says, hey, you're in an overspeed, I mean not overtemp, but overspeed condition, cycle down to 75%. And that's going to cycle our fuel coming into the fuel control unit down to 75%. engine thinks it's fixed itself, it's going to spin back up. So it'll do that until we tell the speed control lever to get out of that position. So it'll just keep going from overspeed to 75, overspeed to 75 until we do something, unless it fixes itself. In most cases, it's not going to fix itself. Much better engine to look at. It's a little cleaner. You can see everything. So just again, the quick recap, the sections. You've got the front frame section, compressor section, combustion, turbine, and exhaust. So now coming back, looking at the engine accessory drive gearbox mounted at the 6 o'clock side of the front frame. Here is that fuel control unit that we couldn't see from the other side. Now this, on the aircraft, what you see here, the alpha beta cables as we call them, these are normally underneath a yellow cover. So they would sit on there like that, and there's a yellow cover that sits over that, so you don't get to see all this, but it's nice that you can see where that's at. So these are part of those things that in the NATOS we say there's 6 things that this fuel control unit senses. Here's 2 of them, the alpha beta, and we'll talk about that. But so now you can see the fuel control unit. This is the solenoid that we left off on number 3 engine. We were saying it received that signal, come across the engine to the solenoid and cycles your fuel control unit down to 75% and then back up. All right. So my fuel control unit, 6 items that it senses. T2, right here from my front frame section, outside air temperature. So these are my T2 coming in, intake into the fuel control unit, or input into the fuel control unit. And if you notice, one of those T2 lines is receiving bleed air. P3 is coming back through. So we're using a little bit of that heat from that compressor discharge, P3, compressor discharge pressure, to kind of stabilize the incoming air into the fuel control unit. So we don't get this really cold burst of air coming in, but yet the engine's already online and it's kind of cycling, doesn't know what to do. All right. The other item that we sense is P3. So if you look right in front of where this one was picking up and coming back to the T2 line, we've got our P3 line that comes down, goes all the way down on the bottom side, and this is where it's being sensed on the fuel control unit right here. This is my P3 line for the input to the fuel control. So right here. And then we said that NG senses NG. So here we had our NG tach generator on the front side of the engine accessory drive gearbox. This is going to send a signal down to my cockpit gauges, instruments. But right here is where I'm actually sensing NG for my fuel control unit. So right here, this is where I'm going to pick up NG readings and sense it. And then I have NF. And again, NG was gas generator speed. NF is free power turbine speed. T2 was outside air temperature. My P3 that was coming in was my compressor discharge pressure. So that's 4 of the 6 that we're going to sense. Last 2 deal with these alpha beta cables. First one is speed control lever positioning. So each one of my engine speed control levers, the upper cable is my alpha. This is my speed control lever. As I move my speed control lever for the respective engine, it's going to get sensed through the gearing to my fuel control unit. And then this one is my load signaling to hold desired NF, or collective bias. So this is where I'm getting that reading for, as I pull my collective up, push my collective down, it's saying, hey, I better spool the engine up because you're asking me to pull a lot more power. Rather than you have to manipulate your engines at the same time you're doing collective, it's doing it for you. So load signaling to hold desired NF. All right, take a peek up here, we can actually see that anti-ice valve on this engine much clearer. So if we look, right there is your anti-ice valve. And if we trace that out, we follow that big line, we can trace that line all the way back out to our compressor discharge pressure. So right here, P3. And here is the cap on number 2 engine. If this was number 1 engine, you would see that line that went off and went down to the bulkhead for the quick disconnect. Again, number 1 and number 3 engine uses compressor discharge pressure for fuel probe extension retraction and to help us with fuel purging. All right. One more thing in the overspeed arena. This is the little box that when I do my overspeed test in the cockpit, I'm going to test my overspeed. This is my switch, my overspeed switch. It's going to cycle my engine, test my overspeed system, make sure it's working fine. So it sits right there underneath your oil tank. Now you can actually see the cutaway of the engine. So again, you can come back and you can see where your front frame section here is, and here are those struts. So this is nice to see that you can see your struts in the front frame section, but more importantly, you can see how the journaling is that's down through, and it allows that hot bleed air to come down through. Not only does it come down through the center of the strut, but it also sends it down through and ducts it back to your inlet guide vane, to your section of your inlet guide vane, to keep these inlet guide vanes anti-iced. All right. And then you can look at your compressor section. Again, from here to here, you get to see your variable inlet guide vane, and you get to see your first 4 stator vanes that are variable, and you get to see the last sections that are not variable, that are fixed. All right. We could pick up to our combustion section. Oops, sorry, right here is your combustor. So now you can kind of look up inside, and you can see that going in there. There's your fuel nozzle. It sits in there. And I don't know if you're picking up, no, you're not. This one here is just a lubrication point that's coming out, but if you lean over and look on this side, you will notice that there's a tube. So unlike the other side where it was lubrication, if this was number 2 engine, you would see it here on that side as you look into the engine. From right here, the front side of the combustion section, all the way back to your power turbine section is a tube. It's using that, again, it's using compressor discharge pressure, because that compressor discharge pressure, even though it's warm, is much cooler than what it is coming back here off the back side of the combustion section. So it'll help to kind of cool the front side of your power turbine, try to prevent us from burning the engine up. And then you can see your thermocouples, your 14 thermocouples that stick down through into your power turbine. And you can see your front section, your gas generator turbine, and your power turbine. So now what I'm going to do is I'm going to rotate. Here's your shaft. So you notice that that spins independent as my power turbine is spinning independent of my gas generator turbine. Now, if I had the strength to roll over the compressor section, we could spin your gas generator, but I don't have that kind of strength. But your gas generator is physically connected to your compressor, so that when your gas generator turbine spins, it is going to spin your compressor section, so now your start motor can stop spinning it and it becomes that self-sustaining engine. On the back side, here you can see that gearing that we talked about, and you can see your little sensor down inside. It's going to tell you when you get overspeed. So if you look right down there, you see this little sensor. That's what's going to signal that you've hit 110% right there. When this thing is spinning fast enough, that's going to send a signal down through that tube. So pull it out, drives it all the way up through, kicks it across, and goes to the solenoid on the fuel control unit. It's going to cycle your engine. As we walk down through the cabin on the bulkheads, we see all these breakaway valves. All right. And the way we look at these, I don't know if you guys have looked at the breakaway valves and been taught to check them, but you notice how it's got a groove right here? So you see that groove? You're looking to see that the top and bottom groove are aligned with one another, and that they should be going in the direction of fuel flow. So in this case, fuel is coming out, so it should be going, so as you can see, that line is in direction of fuel flow. If I see that turned, or I see the upper one displaced from the bottom one, I know there's something going on with this breakaway valve. I'd want to say something to my maintenance guys, have them come check it. They do have limitations. They can rotate slightly, but hard landing, stuff to that nature, can pop these breakaway valves, and we don't know it. We don't realize it. And then we start having little quirky fuel problems in our system. It's because one of the breakaway valves is it's broke itself away, and we didn't see it, didn't check it. So all down through, on both sides of the cabin, or cabin bulkheads, so starboard side, port side, same thing. And then we got these big red valves here. These are called vent valves. So we've got one here, and then we've got 2 back aft. All right. Those vent valves, what they're for is when we're refueling the aircraft out on the refueling control panel, or out on the panel, there's little vent gauges. We tell the crewmen to watch that, monitor that, and if we see any rise in that, we stop the refueling evolution. these are the vent valves that are doing the work to vent our tanks right here, these big red canisters. All right, coming down, we've got a fuel prime pump. This is if, heaven forbid, that we needed to prime an engine. This is where we're going to come in and prime. Typically, all of our maintenance guys, anytime they remove and replace big components on the engine, or they remove and replace a engine, they're going to come in and prime the respective engine. And the way it works is you have to look at your placard, and then you have to set up your fuel selector levers respectively. So here I want the left engine fuel line and cross feed. I'm going to put the number one engine in direct. I'm going to put my other fuel selector levers into the number one tank. So basically what I'm doing here, and then it tells me that my prime valve upper, prime valve cross forward, and prime valve cross upper. All right. So how do I know which one of these is which? I have to go back through and look at my ICW lessons or my CBT lessons, because we've got them clearly marked in there. Or I have to go into my maintenance manuals to make sure that I've got the right ones. So I've got prime valve cross forward upper are here. So cross forward upper, cross forward, and prime valve upper up here. So if I wanted to prime valve upper, number one tank, basically I'm going to open this up and I'm going to wobble. That's going to pull fuel from the number one tank, and it's going to bleed, so to speak, the air out of that fuel line coming from each one of my tanks or from number one tank to each one of my engines. So make sure that I don't have any air from number one. Then I can go through and I can do the number two and number three and so on. Now, as far as the APP goes, there is no valve for the APP. If I want to prime the APE, I have to go in the cockpit, and I just have to simply see if this trainer has, yep, there you go. So my APP is manual. So all I have to do there, and I don't know that we have an APP control, we don't have. All I'd have to do is take my run start lever on my APP control panel and move that run start lever. When I move the run start lever, it's going to open up my fuel valve, and then I can prime. And the key with that, priming the APE, I don't want to go crazy, maybe 3 pumps and that's it. Because once I start it, if I got too much fuel in there, I'm going to have a fire. Close it off. Alright, so we come down below our breakaway valves, near the deck. We've got these things called electrical pre-check valves. These are what make the magic happen for our fuel control system, or for our fuel system. This is what allows us to control how much fuel we put in the tanks. Okay? These electrical pre-check valves in the NATOPS will tell us that the electrical pre-check valves open when electrical power is applied to the aircraft. Well, guess what electrical power applied to the aircraft is? Me pushing the refuel power button on it. Okay, that's why we're kind of anal. If you look in the NATOPS in your checklist, before we start any refueling operations, they want to make sure that up front, you're pushing that button before anybody hooks up to the aircraft. So what you're basically doing is you're telling the electrical pre-check valves to energize in an open position, which basically floods your tanks, your high-level sensors in your tank. So we think of a high-level sensor like a float on the back of our toilet. So we got the toilet bowl, the float. If the electrical pre-check valves are open, then all the water rushing into that tank, or in this case, all the fuel rushing into the fuel tank, is going right to that float. We're going to flood the float, and it's going to think that the tank is full. So now we can't let any fuel come into the aircraft unless we deselect the respective electrical pre-check valve. We do that by the individual tank selection buttons. We push that we want to receive fuel in number one tank. When we push that in button for number one tank, it tells the number one electrical pre-check valve to close, stops flooding the high-level sensor. Now fuel comes through our shutoff valve, fills our tank up, and if we get to, let's say we want to stop at halfway, all we have to do is deselect that tank, electrical pre-check valve opens back up, floods the high-level sensor, tricking it, thinking that the tank is full when it's only half full. So critical for us, very critical, couple things. Critical that we put, before we let anybody hook up to the outside adapter, we put refueling power on to cause each one of our electrical pre-check valves to go into an open position and flood the high-level sensors. And then the other thing is if we do top off, the NATOPS I think has a caution, it may even be a warning in the NATOPS, that if we top off the tanks, to make sure we do not deselect the tanks. because deselecting the tank is going to trigger those electrical pre-check valves to open and allows more fuel to come in to flood the high-level sensor, but there's no room because your tank is already full and will rupture the tank. We learned that the hard way. We learned that the hard way with the MH. We did it many times before we realized what we were doing. And then so we said, we better stop that. So, electrical pre-check valves. And as you see sitting below those, these little valves here, these are all part of that cluster called the purge valves. These are all over the place. I don't even want to try to go through and find all of them, but that's what your purge valves look like. These are the ones that, if you look in the NATOPS, there's some of them that will run for the whole 8.5 minutes. There's some that only open and close for a couple seconds. But they're sequencing all of your fuel to go back into your tanks, using that bleed air to purge back into your tanks. So, it's purge valves. All right. Breakaway valves, you have some more in the overhead here for number 2 engine. So this one is kind of mocking that the manual fuel shutoff valve for number 2 engine sits where the breakaway valves are. That's not necessarily true, because these breakaway valves are near the electrical firewall shutoff valve for number 2 engine. Because remember, number 2 engine, where it sits, your mechanical or your firewall shutoff valve is electrical for number 2, whereas your fuel selector shutoff valve sits in front of the main gearbox in that cabin overhead. So you got that whole distance from the front of the main gearbox all the way back to number 2 engine. It's a fuel line that's full of fuel. So if you want to shut down number 2 engine, you want to shut it down at the firewall, not shutting it down necessarily at the shutoff valve here. Whereas the number 1 and number 3, their fuel selector shutoff valves are right at the bulkheads of the engines. So they don't have to have those electrical, because when you say, hey, I want to secure fuel to that engine, you're shutting it off right at the bulkhead of the engine. But because number 2 engine, you get that extension, that line that goes from the front of the main gearbox all the way back aft, you have to have the electrical shutoff valve for number 2 engine. All right, let's go out and look at the actual tank and show you where the high-level sensors are, stuff of that nature. As we're going out, I want to look at this refueling panel, so you can kind of look at those vent valves. So these are the vent valves we're talking about. If one of those big red canisters was starting to fail, not venting off properly, we would start to notice that pressure increase here. On our procedures, it tells us, I think, or in the NATOP says 1.5. No, any movement on the gauge we know is a no-go. It's not venting. We got to shut it down. The other thing we have out here is we have manual pre-check valves. We have a primary and a secondary manual pre-check valve. And you notice they're in the closed position. These are the same as your electrical pre-check valves. If I run it to the open position, guess what it does? It's going to flood my high-level sensor. Now, I have 2 high-level sensors in each tank, so this one would flood the primary high-level sensor in each tank. This one would flood the secondary high-level sensor in each tank. So now let's go look at a tank and we're going to look at those high-level sensors. So there we can look inside the tank. You can see, and I don't know how long. There you go. See if I can put a light on it as well. That'll help. So there you can see that's your low level. When you're transferring or you're defueling, you got low level sensors, but there's a high level sensor here, and then there's another post in the back of the tank that's got a high level sensor on it as well. All right. So what happens is fuel coming in is going to flood those high level sensors. Now with your electrical pre-check valve, it floods both high level sensors. It's not selective as to whether it goes to primary or secondary. It floods them both. The first high level sensor in the tank to float to trigger is going to stop the refueling. It doesn't wait for both high level sensors. The manual pre-check over there is for us to really truly test to make sure that each high level sensor is working, because when we do it with the electrical, we have no idea that both of them are working. One of them worked, but we don't know that both worked. There we can actually test the primary and the secondary, so we know that each high level sensor in the tank is working. And then your shutoff valve is this big tube coming. It's hard to see this in this tank. There's your shutoff valve right here. This is your shutoff valve. So fuel is coming through this shutoff valve and it's flooding the tank up through. Now, the thing with this, we have a relief valve on this inlet line to the shutoff valve. It's set to pop at 55 psi. That's why it's critical that when we refuel, we set our refueling truck pressure not to exceed 55 psi, 35 to 55 psi. We go above 55 psi, we're bypassing our shutoff valve and we're popping the pre-check valve, and we're just putting gas in the tank and no way of stopping it at all. So don't flood that tank. So critical that we do that. In between each one of our tanks, and we can kind of look back here too and see a little bit more in this aft tank. I don't know if we can get great shots, but you see a little bit more of your shutoff valve here. You see a little bit more of your high-level sensors. But in between each one of our tanks and the sponson, we have our dump/transfer pump, and then we have 4 valves. We have a dump valve, we have a transfer valve, and then we have a respective tank valves, 2 respective tank valves. So the way this works is if you decide you want to transfer fuel from one tank to another. So you want to transfer fuel from, let's say, the number 2 right, you want to kick it back into the number 3. Transfer/dump pump's going to kick on. Each one of the tank valve that's coming out is going to open up. So the number two right tank valve is going to open up. It's going to put the fuel to the pump. Pump is then going to transfer to the transfer valve back to our main fuel line, just as if we were getting gas from the panel over there from the truck. Once it gets into the main fuel line, then it's going to come into the tank during the normal way that it would have before. You select the appropriate tank that you want it to receive in. That tank's not being flooded by the high-level sensor. Fuel's going to come through the shutoff valve, come in until you deselect it or the tank gets full. Okay? Same. Now, if I want to dump it, my transfer/dump pump is going to kick on, and depending on if I select all or select individual tanks, if I select all, then both my tank valves are going to open up. Both tank valves are going to open up, supply fuel to my dump/transfer pump, and my dump valve is going to open up and it's going to dump my fuel overboard. It's going to exhaust it overboard.